Hello everyone, here we'll be finding the volume of this tetrahedron that is bounded by the planes z equals 2, y equals 3, x equals 1, and the plane 3x plus 2y plus z is equal to 4. Now we're going to do this using triple integrals. I'm going to actually check our result using a different method that I'm not going to verify, or I'm not going to justify that method. Maybe in another video, possibly. I'll have to see. But first off, what is a tetrahedron? If you don't know, a tetrahedron is the most simple polyhedra solid, so polyhedron or three-dimensional solid. Basically, it is a triangular base pyramid. So imagine what you normally see for a pyramid, only we have a triangle base. So something like this, and then in the back, maybe we have this triangular base, and then we have this going up here. So there are four sides, and they're each triangles, so this is what that solid would look like. Now to graph this one in particular, we're going to graph this on the x, y, z space, usually oriented like this. Now I'll admit this is actually going to be pretty hard to visualize, but we'll do our best. Now notice that we have the planes x equals 1, y equals 3, and z equals 2. I'll do my best to be as much to scale as possible. Now if we go out to y equals 3 and x equals 1, and then go out to z equals 2 and y equals 3, let me do that actually here in the x dimension as well. So we get kind of these like side walls in this floor, if you will, but now if we extend into actually this dimension here, we end up with this point. Now this point, not surprisingly, is just the point 1, 3, 2. And in fact, if you don't mind over here, I'll call that point P, 1, 3, 2. Now, for any tetrahedron, you can tell it has how many vertices, how many corners. Well, there's 3 here and then that one back. So there's actually 4 corners, or 4 vertices. In other words, there's 4 points. This point will be one of them. Now, it is possible that this plane actually passes through this point. And that would be bad because it would be not really a tetrahedron, in which case, actually, there would be, well, the volume would be 0. But you can see if you actually plug in these values into this, you don't get equality. You get like 9 equals, it wouldn't be 9, I guess it would be 3 or something, sorry, it'd be 11 or something like that, equals 4, which isn't true. So in other words, this point is not on this plane. So now what we're going to do is to find the other points, we're going to basically plug in 2 of these values at a time to see what the other value is. I'm going to write the resulting points, and then we'll attempt to plot them and try to visualize what the tetrahedron looks like. And I'll call those points Q, R, and S. So those other 3 points, Q, R, and S, just going in alphabetical order, I suppose. Now, when x is equal to 1 and y is equal to 3, what is z? Well, if you plug in x equals 1 and y equals 3, you get 3 plus 6, that's 9. Subtract 9 to the other side, z is equal to -5. Okay, good. What about when x is equal to 1 and z is equal to 2? What must y be? So when z is 2 and when x is 1, and here we get 3 plus 2, so that's, notice that's 5. Subtract 5, 4 minus 5 is -1, divide by 2, we get -1/2 for y. Okay, and now finally, the last scenario, what if y and z are 3 and 2 respectively? What is the x value? Well, if you let y equals 3 and z equals 2, this becomes 6 plus 2, which is 8. Subtract 8, we get 4 minus 8 is -4, divide by 3, x is equal to -4/3. So these points will actually be pretty important later on. But for right now, to try to get an idea as far as what this looks like, it's not going to be quite to scale, but just bear with me. In fact, just so it's a little to scale, let me try to lower this box a bit. Because notice 1, 3, -5, 1, 3 is actually this line here, and then the z values can vary along this line. So if z is equal to -5, it's actually way below this point here on that line. So imagine this is the point, so this is P, imagine this is the point Q. Okay, 1, -2, not 1, -1/2, 2 for R, well let's see, the x value is 1, that's fine. The y value is -1/2, which is in the negative y direction. So it's going to be a little bit over here, let's say. And now we're going to go up to z equals 2, which is along this part. So it's going to be over here. Good. 2 more to go. Actually, no, we have 3 points, so 1 more to go. Good. So negative 4/3, 3 and 2. If x is negative 4/3, it's in the negative x direction, which is over here. Negative 4/3 is, let's say, about there. And then y is equal to 3, and z is equal to 2. So I hope we see how I'm getting these. It's a little hard to follow because of the 3-dimension aspect of things. But these are these 3 points. And if we connect all of the points together in such a way to develop this tetrahedron shape, we end up getting this magical thing right here. There we go. Now the top plane, as it turns out, is indeed a section. So the top triangular side is a section of the plane z is equal to 2. So for the triple integral, well, recall first off that volume of a region, let's call it E, is equal to the triple integral over E dv. In other words, the integrand will just be 1. So now to set up this triple integral, what we're going to do is we're going to set up an iterated triple integral. So I'm going to space it out a bit because the limits will be quite long. Well, a few of them will be long. Now let's do z first. So if you look at z at most is going to be at z equals 2 because that's the upper part of this tetrahedron. The lowest z can be is actually on this slanted plane that's actually on the other side of this point, kind of on the other side. There are the points out here, imagine. Again, it's hard to visualize because of the 3-dimensional aspect. So if we solve for z on this plane, we get 4 minus 2y minus 3x. So solve for z, that's what you get. So we're going to do dz first. Then we'll do dy, and then we'll do dx. Now, to discuss dy and dx, well, dx we can actually do not too bad. But to discuss dy, really what we should do is we should project to the xy plane. Now, when we project to the xy plane, there's a small triangular section here that is the cross section when projecting to the xy plane. That's not what I'm talking about. What I'm talking about is this projection, the actual shadow, which is this entire cutout here. Now, really what we should do is let z equals 2. Because notice that shadow is exactly equal to this side when z is equal to 2. So if we let z equal to 2 here, we can solve for, well, in fact, I won't really solve for it, but I'll just say this. When z is equal to 2, we get the following. We get 3x plus 2y plus 2 equals 4, subtract 2, we get equals 2. Now, the reason why I'm not going to actually solve anything here is because if we just consider the xy plane, it's kind of the xy plane because really it's the plane z equals 2. So if you want to call this z equals 2, that's fine. When y is equal to 3, we have this line here. X is equal to 1 is this line here, let's say. Okay. And now to actually find out what this line corresponds to, we can just find x and y intercepts. So if we want to find the y-intercept, just cover x. When x is 0, 2y is equal to 2 divided by 2, y is 1. Okay, to find the x-intercept, that's not too bad. Set y equal to 0, so then x would be 2/3, which is a little bit over that way. So something like that. Okay, good. So now we're going to ask ourselves, at this point, what does this point represent? We actually already know what it represents. Because here, y is equal to 3, and z is equal to 2. And when y is 3 and z is 2, the point that we have on the tetrahedron is not 1, 3, 2, that's this one. We want, I think, this one here. Let me see, y is 3, z is 2. Yeah, it would actually be this point, I'm sorry. Again, the visualization is a little hard. But y is 3, z is 2, we have this point. So the x value, notice, is going to be negative, and it is indeed negative 4/3. So the x value here is negative 4/3. The y value, the x value here is 1. So for x's, we're going from negative 4/3 to 1. So we can actually develop the x limits quite nicely. And this tells us that we're going to be doing dx last, which we kind of already had the idea of. And now where do the y values go in this region? Well, the highest these y values can be is 3. The lowest they can be in between these x values is on this line. So this line is essentially the lower limit of points here in between these x values. So if we solve for y here, we'll get 2y is equal to 2 minus 3x. And then of course dividing by 2, we get y is equal to 1 minus 3 over 2x, like that. So that's our lower limit, 1 minus 3 halves x. Okay, so this is the setup, this is what took the most time. Now what we're going to do is just integrate. So I'm going to erase all of this and then we're going to integrate now. All right, so again, there's a lot actually going on here. The derivative or antiderivative with respect to z of this integral, remember the integrand really is 1. This actually is not too bad because antiderivative of 1 with respect to z is just z. And then subtracting these when you plug them into z is really just 2 minus this quantity. So if we distribute the negative, those become positive. 2 minus 4 is negative 2. So really we have this double integral now with our integrand now being 3x plus 2y minus 2. That's not too hard to verify. First dy, then dx. We know the limits. 1 minus 3 halves x to 3, there we go. And negative 4 thirds to 1. Perfect. Now what? Well, now we have to take the antiderivative of this with respect to y, which I'm going to work on quite a bit here below, and then we'll continue the integral. So first off, let's treat this 3x minus 2 as a constant. And its antiderivative with respect to y is just itself times y. Antiderivative of 2y is just y squared. That makes sense? Now we want to evaluate this between the limits. So we want to plug in 3, then plug in 1 minus 3 halves x. There are a lot of ways of doing this, but the best way of doing it is the following. So plugging in 3 is not too bad. When you plug in 3 for y, you get 3, distribute that, we get 9x minus 6 plus 3 squared is 9. So these actually combine to just 3. Negative 6 plus 9 is positive 3. So that's not too bad. But now what? Well, now we have to plug in this 1 minus 3 halves x into y, and then do this minus that quantity. So the first thing to notice is that we're going to have 3x minus 2 times 1 minus 3 halves x plus 1 minus 3 halves x quantity squared. So let me just border that off for a bit. Kind of intersect that a little bit. Now look inside here. Something we can do, notice, is we can actually pull out this common factor of 1 minus 3 halves x. That would just be the same as factoring out a y. Now you don't have to do it this way, but I think this is probably makes it a little simpler, I think. So pulling this out, what we have left over from the first term is 3x minus 2. What we have left over from the second term is just 1 minus 3 halves x. And notice negative 2 plus 1 is negative 1. And 3 minus 3 halves is 3 halves itself, so that's going to be 3 halves x. Now before we jump the gun and think this is like a difference of squares or anything like that, really these are kind of the same. And with this negative in front, we can actually distribute the negative here to make this a positive, so that these are indeed the same. Meaning this will just be that quantity squared. So in fact, all we have really is 9x plus 3 times this quantity squared. And if you FOIL it out, which we now can do, and I'm just going to be doing, you can do it like this if you want, but I'm going to do it just looking at this. So it's the first one squared, 1. 2 times their product is negative 3x. The last one squared is 9 over 4x squared. Perfect. Awesome. So now what we have to do is combine things. These combine to 6x, these combine to 4. That's our integrand now. So now our integrand here from negative 4 thirds to 1 dx, so the x integral finally, will have integrand 9 fourths x squared, 9x minus 3x is positive 6x, and then 3 plus 1 is 4 dx. Good. So all this scratch work just to get from here to here, that was the first, well, not first integral, but that was the second integral. Good. So now what? Well, now I'm going to erase this, and then we're going to continue this integral, and that's going to finish it off, and we'll get a nice value, hopefully. All right, so now finally, we're going to take the antiderivative of this with respect to x. That's actually not going to be too bad. The antiderivative of this will be x to the third over 3, but 9 over 3, notice, is just 3. So that's going to be 3 over 4x to the 3. Oh, that was okay to follow. Right, because 1/3 times 9 fourths, the 9 and 3 cross cancel to 3. Good. Antiderivative of 6x is 1/2 x squared times 6. Half of 6 is 3. So this is actually 3x squared. Antiderivative of 4 with respect to x is 4x. Now we're going to evaluate this between our x limits, negative 4 thirds and 1. When you plug in 1, you just get the numbers in front. So notice that's just 7 plus 3/4, so that's 7 3/4, like this. Minus, so I'm going to use this mixed number notation, maybe that'll help the evaluation a little bit, but we'll see. Minus, what do we get when you plug in -4/3? Geez. Well, 3/4 times 4/3 to the third is 4 to the 3 over 3 to the 3, but it's negative because it's a negative value to an odd power. And notice 4 goes into that 4 squared times 3 goes into that 3 squared times. So this is actually -16/9, if that makes sense. When you plug it in here, you get 3 times 4 squared over 3 squared. That goes into that 3 to the 1 times, so that's plus 16/3. Right. And now let me just check here. Now the reason why this is true is basically because when you take a negative number to an even power, the negative goes away basically. So I hope that's okay. Now when we plug in here, 4 times -4/3 is -16/3. Well, that's actually interesting because these actually cancel out. Okay. Now what? So now all we really have left is 7 3/4 plus 16/9. Now 16/9 is a mixed number. 9 goes into 16 once, so that's going to be 1 7/9. So we got 7 3/4 plus 1 7/9. If you combine the 1 and 7, you get 8 and whatever those fractions add to. So now if we add these fractions, I'll do this off to the side here. I'm going to use this kind of crisscross pattern of adding fractions. Multiply opposite denominators to opposite numerators. Multiply the denominators to each other. We get 9 times 3, which is 27. Plus 4 times 7, which is 28. I think this works so far. All over 4 times 9, which is 63. So if you add these together, we actually get 56. I think that sounds good. I'm sorry, 55. It's 55. I knew something was up. Perfect. Now, of course, this is a mixed number itself. This is 1 and something over 36. And in fact, it's just the difference between them. Okay, so what's the difference between 55 and 36? It's 19, I think. Yeah, that checks out. And now, if you add this 1 and 19 over 36 to 8, we get our answer finally, which is 9 and 19 over 36. Now, if you wanted to write this as one fraction, then you can just convert this back into an improper fraction by multiplying 36 to 9 and then adding 19. Now, I'll actually show that after the fact, but for right now, I'm going to call this our answer, and hopefully this agrees with what we're going to get doing a different method. So I'm going to actually verify this using a different method that I won't justify, but I'll show you anyways. It's going to be quite nice. So let's take a look at that right now. All right, so here it is. This is the answer we just got, 9 and 19 over 36. We recall our vertices are P, Q, R, and S. They were these values, or these points, really. Our verification method is something I looked online, and there's this formula for the volume of a tetrahedron. It's actually quite nice. It is 1/6 times the determinant of the matrix, 4x4 matrix, whose entries are the points and then 1 for the last row, or for the last column, I should say. So our points, notice, are these points exactly. So I have X, Y, and Z for each of these. And then the last entries here for the column, the fourth column, are just all ones. Now it's interesting why this formula is a thing. Now I'd imagine that there's actually a way to prove this using the method of triple integrals. So yeah, that would make for a nice video. So maybe we'll do that in the future, which is nice. But this is actually pretty cool because we can verify this pretty quickly using our calculators. Or if you want to take the determinant is 4x4 by hand, good luck to you. You can try that if you want. I'm not going to do that though. But yeah, if you do that, do that. And I did this in my calculator and I got 343 over 6. Well, that times 1/6 is 343 over 36. And if we wrote this as an improper fraction and got 343 in the numerator, we'd be set. Now remember that to convert a mixed number to an improper fraction, you multiply the denominator to the big number and then add to the numerator. And that of course works because this is really 9 plus that. You can write 9 as 9 over 1, multiply top and bottom by 36, and you end up with 9 times 36 plus 19 anyways. Now there's a lot of really nice ways of doing this, but something I want to kind of recognize is that notice 19 is just 18 plus 1. Also notice 18 is 9 times 2. And if we actually factor 9 out of this, we get 36 plus 2, which is 38, then plus 1. Also notice 38 is 40 minus 2. So I know this is like really, really wacky, but this is just, I think, kind of nice to see maybe. 9 times 40 is 360, 9 times 2 is 18, and then these two combine to 17, negative 17 in fact. So we get 360 minus 17, and look at that, that is indeed 343. Which, by the way, I think is 7 cubed, which is kind of interesting. So yeah, you can kind of take a look into that if you like. But yeah. Good, we verified that this is indeed our answer. Nice. And we saw this new method now to find the volume of a tetrahedron if you know the vertices of that tetrahedron. Again, this method is still a little weird because I haven't justified it, but maybe we'll do that, like I said. I don't know. So I hope you enjoyed this video. That was kind of nice. We found this using triple integrals. And the integrals weren't that bad, but the setup is what is making this problem a little difficult. The visualization, I hope, helped. So, like I said, thank you for watching. If you want to watch more of my videos, watch my videos. And if you do, I'll see you then.